So, we talked about then the first thing, a hit signal detection theory being correct identification of a target as old, at least in our memory context, right? So, I want to remind you guys what this stuff is because this is going to play a key part in helping you guys to work with the data and to help to create hypotheses and know the conditions that you want to compare against each other and stuff like that as we're building along through the course. So, you got that. So, somebody else, what is a miss in signal detection theory? Yes?
Well, in the relation to our experiment, if you answer it that it's an old word, it's actually a new word. So, in other words, or the other way around?
Yeah.
Yeah, when you answer it's a new word, it's an old word.
Exactly. So, if you can always think about basically two factors in determining these things, right? What is it really? And what did you think it was? Or perception versus reality. So, if it's a miss, what's the reality of it? What is the reality of a miss? What was it really? You just said.
Yeah.
What is it?
What do you mean?
What is? You see a word on the screen. Whatever that word is. And we know that it ends up becoming a miss in your experiment. What does that mean? What was this in reality?
So it was actually an old word.
It was really an old word, yes. So it was really an old item, but what did you call it?
Oh, a new word.
So you perceived it as
Something new.
a new word. Okay, so we had that as a miss. Okay, so that was the second question. What about a correct rejection? Yes, Kelsey.
Correct rejection is when you basically in our experiment correctly identified a new word as new. So it wasn't the target you were looking for, and you spotted it as such.
Exactly. So it's a correct rejection of what you're seeing as not being old. So that sounds like a clunky way of saying something, right? But it's basically saying that a new item is new. Now that's obviously going to be correct when you say that, so you can call it that you're correctly rejecting it. So sometimes people refer to new items in memory studies as lures or foils. So either way, you can call it any of those things, you're correctly rejecting it as a lure, trying to get you to say it's old, even though it's not. Make sense? Okay, so pretty straightforward. We covered a lot of that stuff in class last time we met. So, let's see. Next question was, identify 3 types of artifacts in EEG that we typically find, and identify at least one thing for each that we do to either prevent them from occurring or to deal with them once they do occur. So for this, obviously, you get 1 point for each of the artifacts that you identified, and 1 point for each of the, what you might call prevention or cure of them when we see them. So we covered more than 3 in class, so I was trying to be nice and put you guys up here with some flexibility to have forgotten 1 or 2. So hopefully you were able to remember at least 3 out of the 5 or 6 that we talked about. So who can think of one type of artifact that we talked about? Yes? Okay, blinking, right? So here's a marker. Would you like to draw us what a blink might look like? What?
Kelsey can do it.
You're going to phone a friend? Okay, Kelsey, come on up and draw a blink.
So kind of have your just your regular like kind of data, and then blink is like this.
It could be, yeah, but you got to add one little element to that, right? How do we know that that's not brain activity going up really high? How? What? There is a lower one that goes along with it, yes. Right? Well, it's not going to be on the same trace. It would have to be on a different trace, right? Because you have an upper eye electrode and a bottom eye electrode. Okay, there you go. So those are 2 key features in the EEG that help us to identify what we're seeing. But there's a third little part. I want to see if any of you guys can think of what else needs to be added to this. How do we know that those are not brain activity? Because it's perfectly possible, right? That could be the brain thinking of something or doing something. Yeah.
Like that is straight.
I wasn't thinking about a straight line yet.
It's a location, right?
Location, okay, yes.
How when you're looking at the entire data, it goes and it affects multiple areas of the scalp.
Yes, but that could be neural too. Because let's say that something, a light bulb happens right here, and it just goes, and I'm really thinking of something good, and it's happening right here, hypothetically, right? That's still going to spread to the other sites around it as neural activity, just like our eye activity is also going to spread to the sites around it. So that in itself, just knowing that it's affecting other sites around it, doesn't help us to distinguish whether or not it is neural or an artifact. But I like what you guys were saying over here, ladies, about there have to be some information of location, right? What I'm thinking of is you need to put one more, maybe two more pieces of information that lets us know where are these sites of activity being recorded from. Yeah, but we wouldn't, exactly. So all I'm looking for is a little bit of a label on the left-hand side, but you wouldn't label it with a F1 or AF1 for anterior frontal one, would you? You label it the vertical electrooculogram and VEOG. And you could also have the VEOGL, the lower one. VEOG lower.
Did we talk about that?
Come again?
Did we talk about that?
No. We're just adding.
Okay.
You didn't need the letters and all that. Obviously, you didn't even have to draw it for the quiz. I'm just building upon what you know.
What does VEOG mean?
VEOG, actually, we did talk about it when we looked at those big screens of EEG going all the way across the screen. And we said that there's labels, and remember we talked about the 1020 system? And then we said, what are these bottom electrodes where we can see the eye blinks? And we said there was vertical electrooculograms, and then there's also the horizontal ones. Remember?
It's like the saccade over there?
Yeah, exactly. So that brings us. Good job, Kelsey.
I was gonna say, can I draw the other one where it's everyone's reading?
Now we gotta have other people draw the next one. So yes, right. I don't know. Oh, you got one. Okay. So what is another one?
Basically, when the people like that, you know, they like squint, you know, because they're trying to think of something.
Muscle tension.
Yeah, and then like you'll have probably noise in the frontal area.
Yeah. So what do we call that artifact? What would noise be due to muscle tension? EMG, electromyogram. Right. So how would that, can you draw us what that might look like? Now, you want to phone a friend?
Yeah.
Okay, phone a friend. No? Nobody wants to draw some EMG?
I can't remember. Wait, I have them. I can draw it. Yeah, I can draw it.
Kelsey, come on up.
Hey, I can at least draw a squiggly line. I can draw very little.
Yeah, this is the easiest one to draw.
Okay.
Well, kind of. Actually, there's a couple other easy
It's
ones.
EMG.
EMG.
This one's just.
Why is there no G? Yeah, the G there. That's the OG. That's the original G. Okay? The gram, the electrocardiogram. Okay, so what are we looking at here? Right? What is this? Explain the features.
Kind of like, because it always kind of looks very like. Then squiggly, this kind of maybe when you get some muscle tension.
Well, okay. Right? But this would be the muscle tension. This would all be the high frequency muscle tension nodes. In that regard.
So it'd be like kind of like low frequency if it was less tension.
No, it wouldn't the frequency, but amplitude maybe.
Okay.
Really high. So what's the difference between frequency and amplitude in this graph?
Which is negative.
Yeah. So the frequency is it
How many
slow
times
or
you
is
get
it?
weight?
Yeah. So tension is not necessarily indicated by low frequencies. It would be certainly higher frequencies, but also we would see it when we would see greater elements of it, greater degrees of it, we would probably see it in the amplitude, not the frequency changes. Good job.
We're just going over the
Yep. Good job. Okay, so what are some other ones? We'll give Kelsey a break. Guess what? What's another artifact? EKG. Okay. So EKG, you know what that looks like? You want to draw that one for us? Okay. Thank you, sir. Over here. Like that, right? Yep. Now, what is EKG? What is that referring to?
Heart rate?
Heart rate. Yeah. So electro what? Carpet? What? What did you say? Carpet? South Park? Yeah.
Electrocardiogram.
So you're okay.
Yeah. Since you're
Oh, okay.
Good job. Okay, so George,
Yes.
when we were talking about the VEOG and the VEOG lower, you mentioned another artifact a few minutes ago that would be tapped into particularly by the HVOGs. Do you remember what you said?
No.
No? Man, I do.
No, the cicada.
Saccades, yeah, okay, so saccades are another artifact that we talked about, right?
Okay, yeah.
Do you want to draw us what they might look
I
like?
don't remember, but I know it's it gives the eyes and where it hits, so movement, right?
Yeah, I'm sorry. So it was what?
Eye, like where your eyes go. If
Yeah.
your head moves that way, your eyes go that way.
Yeah, so instead of the blinks being when they're your eyelids, so blinks are not actually eyes, right? It's actually muscles of eyelids. HEOG is actually movement of the eyes horizontally. That's the H, right? And of course that's actually reflecting some muscle activity too, right? Because you have the muscles on the side of the eyes making that happen. But the eyes themselves are moving this time. And so you're right, if you're reading left to right on the screen, or you're looking around, or whatever, you're going to have these artifacts, HEOG, these saccades. So, anybody know what the saccades would look like? Kelsey, we're going to give you a rest.
I'm like ready. I'm like.
I know, this is great. We'll see if anybody, yes, can you draw us what the saccade would look like? All right. Do you want blue or green? Blue, okay. All right, so we have a saccade that we're going to see. No pun intended. Okay, so yeah, where's our labels going to be on that too? What sites are we looking at that activity for? Good. Okay, so just like we labeled the links up there, we got to label something like this, right? Because we still don't know. Maybe this is brain activity. It'd be pretty weird brain activity, wouldn't it? But we still don't know exactly. One of the ways that I'm trying to get us to think about this is that when we look at these electrical traces, we can use a lot of clues in order to figure out what it means. And one of the big clues that we can use is which site on the head do we know that it was recorded from? That is, location. That gives us a lot of insight. And so, what are the locations that we should label this from? So, do you remember what George and I were just talking about? Okay, so if we have these here, this is what? V, E, O, G. Remember what those stands for? So what does G stand for? Gram. Okay, so we'll work backwards. So let's talk about the I's here. What do you think the O stands for? Ocular. Okay. Any guess on what E means in our class about electrical things? Yeah, so it's an electro-ocular So instead of EEG, it's an electrical measurement gram of the ocular activity. So it's electrical. And the V means that's the vertical one. It means the one vertically above the eye. The L means it's lower. So if you're going to measure horizontal eye movements, which is what saccades are, these change a little bit, right? It's a different site that we're recording from.
Would be an E.
Yeah. HUG. Good job. And this one would be too, right? And in fact, one of them would probably, you could even label it right and left. Or R and L. Right? Because you would have one on each side. So when one eye goes this way, it's a contraction of one eye, or one eye, excuse me. When you look this way, one eye is going to contract and one is going to relax a little bit, right? So that's why they're going to be in opposite directions.
R and L would be subscription.
Yeah, either way, I mean, you can do it kind of however you want. Good job. All right. Okay, so any other artifacts? Yes?
Did you say something about alpha? Like at the end?
I
I
did.
didn't write it down. I remember saying alpha, so I wrote alpha, but I
Yeah.
don't remember why.
I said alpha is kind of this sort of a little bit of both. So some people consider it an artifact if it's not really what they're looking for, because a lot of times it might reflect basically when you're about to go to sleep, very drowsy and things like that. Other times you might be actually having hypotheses about alpha. Particularly, let's say that you study attention. Maybe you want to study ADHD in people. Alpha turns out to be a frequency of activity that is very, very closely related and very much correlated with states of attention. And so in that case, you wouldn't call it an artifact then. That's actually your variable of interest. Because you want to see how your manipulations in your experiment that are going to either raise attention or lower attention, or how your manipulations between groups of people who say have ADHD or don't have ADHD. You want to see how those different variables are going to affect alpha, for example. So you definitely want to keep that sucker in there then. So it can be an artifact sometimes, but it kind of depends. Like a lot in life, right? Yes?
I'm confused, what's alpha?
Alpha is a frequency of activity. So it was, we talked about it a little bit last class, and it's in the text, but basically if you plot frequency over time, it's an easy way to conceptualize it, okay? So here's your frequency. Okay, and we measure that in hertz, okay? Just like any y-axis, you're going to have different values, right? And so we can start to characterize the frequency, which is how fast or slow a particular wave takes to sort of recycle. If you go from start to finish, a sine wave, right? So it can be a very slow wave, like that, or it can be a very fast wave, where it cycles back lots of times, right? And let's call this, basically a slow wave and a fast wave, okay? You can characterize that in different in measurements. So let's just say we have about 4 hertz here. Let's call this 8 hertz. Let's call this 12 hertz. Let's call this 20 hertz. Okay. Let's call this 40 hertz. Okay. So from 8 to 4 over time, this is basically what we call theta. Okay, now to your question, what is alpha? It tends to be about this frequency. About 8 to 12 hertz. You come up a little higher, say about 12 to 20. Beta. And as you get higher, you're going to have gamma. And up at about 60 hertz, you're going to have a different type of artifact called line noise. Anybody know what line noise is? No electrical engineers in the house? So up here at 60, you're going to have a certain frequency of activity that's very, very high. And what that is basically the frequency of your lights in the room. So when we record brain activity in humans, our brains never produce activity that's 60 hertz for the most part. That's very, very fast. And if you see that, and even if they did, we would not be able to measure it because when we record it, we also record electrical magnetic activity coming down from the lights. And they tend to oscillate at about 60 hertz. So that's the hertz of the line of electricity from the light. So that's one more artifact we can add to the mix. Okay. So does that help? And so when we talk about these different frequencies, we're talking about frequencies of oscillations. So we'll look into oscillatory analyses later on towards the second half of the class, and you can start. We'll show you how you can analyze these different frequency bands to look for different correspondences to cognitive states. And even down here is delta. Okay, so delta often involved in different patterns of sleep, attention, and alpha a lot. Theta is involved in memory a lot. Beta is also involved in memory and a handful of other functions. Gamma does a lot of stuff as well. There's a lot of theta, gamma coupling, so they'll be coupled together.
The gamma kind of tends to get seen as sort of being part of memory.
Yeah, it's part of memory, it's part of a lot of functions. And to be honest, these different frequencies can support communication between different brain areas for lots of different functions. And really, it's kind of still an area of wide exploration in the field. We're trying to fully characterize this stuff. So, It's almost like the Wild West, but not quite that.
I was like thinking about it like last night, just kind of chilling, and I was thinking about how, like when we're talking about artifacts, it makes me think of kind of how you have a computer, right? And you want a specific program open in that computer, but when you think about a computer, there's a lot of other stuff going on, a lot of other hardware and software running on your computer. But you're only really focused on that one program. You only really want to play that one video game. So if you think about it, artifacts are like that software you don't care about, that you're just like, yeah, sure, keep doing you, but I don't care.
Yeah,
But like,
it's a good way to think about it.
yeah.
Okay, so we talked about some of these now, and other parts of the question were ways to deal with these things. So if you see blinks in the data, what's one thing you can do to either prevent it or to cure it once you see it? Yes, Kelsey?
Tell your participant not to blink when they're looking at the word.
Yep.
And like, that's kind of, is that also part of why you can give them a little focus, a little cross? Because it gives you someone to look, but also like, hey, you can blink now.
Yes. Okay, Ryan, what's a way that you can deal with it if they happen to do blink?
Well, you do high pass filtering.
Ooh, I don't know about high pass filtering.
Not for iPhones.
Not for iPhones. High pass filtering would be for drift. So we didn't talk about drift in here. Drift would be a really, really slow wave. It'd be like, let's say, a rising phase of this, but on such a slow frequency. Not today, we didn't talk about drift.
No.
So high pass filtering would be the way that you would account for drift or things like that. The way that you could account for the eye blinks after the fact is to either reject the trials, you just say, nope, we're not including them, or two, we could correct the trials using something like ICM. So we'll talk about that a little bit more too. So let's move to the other eye activity. You can basically do the same, well, actually a little bit different preventatively, right? Yes, Kelsey, what could you do to account for?
Make the word big enough so that they don't have to like.
Or small enough, actually.
Or small.
Yeah, you want to make the word smaller so that they don't have to shift their eyes back and forth. Anybody have an idea for what you would do to deal with EMG? Yes, sir. Tell them to relax, yeah. You might instruct them. Try not to clench your jaw. Try not to crunch your forehead. Yes?
Like, don't react, like facial lines.
Yeah, you want to, this is why we do those practice sessions, right?
Yeah.
Practice with them about it. Sometimes they're not going to know they're doing it, so when we're in there practicing with them, we're going to exercise good experimenter skills and notice, oh, I see that you happen to be punching a little bit and really trying to figure out what you can remember. Try to remember, but try not to, crunch up your forehead while you're doing that, because you might not notice that you're doing that.
So when you're doing that, when you're doing an experiment with a person punching you, that like you're sitting there looking at the EEG and you start to see that?
Well, you don't have to look at the EEG to know that they're clenching their forehead. If you're practicing with them, your eyeballs are looking at their forehead. And you're doing these experimenter skills of working with them during the practice session and picking up on the things that you know you're going to need to have clarified later on. One other thing we didn't get to last class, talking about ways to accommodate EMG, because there's going to be an element of noise in all of our EEG all the time, particularly muscle noise. One way that we get around that is the simple averaging process of the ERP. So if you have, that's one of the whole ideas behind event-related potential averaging. We talked about it in biopsychology. We talked about it in behavioral neuroscience. We talked about it earlier in class for this course as well. Is that if you have hundreds of trials, if you have enough trials, you can average them together, so that the idea is that the noise will wash out over the average process, and you'll be left with whatever the neural signal is that's the same among all those trials that are averaged. But you need a lot of those trials in order to achieve that. Okay? And that's one of the reasons why we have so many trials, so that we can be well suited for dealing with that noise that's inherently big. Okay, so that's pretty good. Okay, last one, briefly, describe the difference between recollection and familiarity. You've been all over this today. Let's see if we can get somebody else. Anybody remember something that they might have put down as some? There's lots of ways that recollection and familiarity differ. What's one way that you might one parameter or dimension by which they differ? Yes or no?
Recollection is when you're like absolutely sure that you've seen it before, or that you've never seen it before. Yes, that's like it's like an older new word. And yeah.
And familiarity is?
Familiarity is, the way I look at it, is like it's like a 2 or a 4 on the scale. It's like you're fairly sure that you've seen it or not seen it.
Yeah, pretty much. So they differ on a dimension of confidence, for example, right? When you're really highly confident, that tends to be reflecting use of recollection. But when you're less confident, it's more reflective of familiarity. Now, the little correction I would add to that is that recollection isn't really thought to be reflected by the ones on the scale or the new items. It's just that you can't recollect a new item, but you can recollect an old item.
Right.
Same thing like the familiarity is going to be those middle levels of confidence that you did say accurately. It's just they're not going to be on the new side. Those are because when you say new and it's an old item, right, you're forgetting. And so you can't be forgetting at the same time that you're recollecting. Or, you know what I'm saying? So just be careful about that little nuance difference. Okay, Lovett, did you have a question? Sorry, hand up.
I'm just gonna.
Okay, yes.
Doesn't recollection also have to be source? Like they know where it comes from, as opposed to familiarity. They see it, they kind of know it, but they don't know where they've seen it from before.
Exactly.
Source versus item.
So there's another dimension that you could say as an answer for this that they differ upon, which is, as Ventura said, you can use source memory to reflect recollection, but at a more specific level, we could say that recollection is referring to the times when we can retrieve the context. The what, the where, the who, those contextual details of that item's previous episode that we experienced. Okay? And so the familiarity, on the other hand, would be retrieval of that item information, but without the context. So you just know that you've seen that thing before. You just don't know where or when or how. And so we can start to characterize these different memory experiences based upon the context.
Oh, I was gonna say, I didn't right out of part. But, for one thing I was starting to put is for familiarity, it's at about 400 to about 500 milliseconds, whereas recollection occurs at about 600 to 900 milliseconds. And I remember that they tend to refer to familiarity as the N400, and then they refer to recollection, that word for a second, recollection as the LPC.
Exactly. That's another dimension that they differ in. They're electrophysiological properties. That is the electrophysiological correlates of these different types of cognitive experiences. Familiarity tends to correspond with the early mid-frontal effect that happens about 300 to 500 milliseconds, whereas recollection tends to correspond with a left parietal effect about 600 to 900 milliseconds. So they differ in both their temporal and spatial distributions on the scale. Okay, that's a lot of good stuff. So it sounds like you guys did pretty good on the quiz. I'll take a crack at them when we're done and get back to you and put them up on Blackboard and all that for you. Were there any other questions about the quiz before we move on? Okay.
Not about the quiz, but I didn't get invited to the Google.
You didn't get invited to the Google
Well, I
thing.
didn't get your email, she forwarded it to you, but I still have to.
Which email? Today? Really? That was just sent as an announcement to the whole Blackboard thing. So you didn't get the announcement from Blackboard? Goodness, okay, I'll give it to you. No problem. Thanks for letting me know. All right. Well, but that's because it went to your CSUSB email, not your Gmail. So the request I got from you was from your Gmail. But either way, I gave you access, so you should be good.
What? It's Lovett, right?
Sign up.
Shit check, I kept a shit check. That's what I said to her,
Okay, so just to kind of review a little bit about what we were talking about then, I'll give you a quick little primer on these artifacts, and then maybe we can dive into some data. Okay, so just to review for you guys a little bit, we had talked about this. Can you guys see the screen okay? You guys want to turn the lights off? Do you mind grabbing those lights in the back? Thank you. Okay, so we talked about artifacts, right? So you can have all these different patterns of ERPs, or at least of EEG activity, that can happen at all of our different electrode sites on the head. And we can see for one thing that in, let's say, a blink, so you guys did a really good job of drawing that. You have this big, huge positive deflection, a corresponding negative deflection as well. Okay? When you have this big blink happen, we can see that it spreads to other areas that are close to it. It's going to happen there. It's going to spread a little bit to these further areas, more posteriorly and then more laterally to the temporal sites. And one of the things that this figure is really nice in showing is that whereas it does spread to our other sites on the head, notice how the further away you get, the smaller the effect is that spreads. You guys notice that? So when you're really close, that's a bigger bump. The bump here gets a little smaller and a little smaller even more when you go to the posterior sites, the central sites. Okay? So a lot of that is because there's basically this, there's a decay function, which is basically the rate at which the electrical activity will decay as it spreads through basically human scalp tissue is a relatively constant function. And so one of the things that you can do is you can use that rate of decay to then work backwards to say that if I know that there's an effect here that's not true, the brain activity, it's an artifact, and you can subtract it from all the different sites at a proportional level based on that decay function. We'll talk about that and how we use that to correct for artifacts a little bit later in today's conversation. So, and we can see these other functions here too. So again, we can have that big blink. We can look at these looking left, right, or saccades, okay? And we can see how they're going to be reflected in our frontal or temporal electrodes that are going to reflect that. Okay, so this might be frontal or temporal activity that you might otherwise think, oh wow, that's the brain acting funky. The brain's really active here, or the brain's really active here. But really what it is, it's a vertical ocular movement, or a horizontal one, that we can know based upon that trace. So it's really useful, because then we can correct or subtract it. But if we don't do that, if we let these artifacts slip into our data that we end up using, then you guys can hopefully appreciate the contamination of the data that we have, right? Okay. And so this is some examples of what we looked at before when we walked through some traces. Okay, you're going to have this blink here, and it might look like a big jump in activity at these frontal sites. It gets a little smaller and even a little smaller as you go frontal, central, and then of course parietal. Okay, so we have that, and we can also do the things that we talked about to try to minimize the blink. Okay, you want to take some breaks. You want to instruct them. When is it okay to blink, and when do you not want to blink? Things like that. And then one little thing that you might instruct subjects is if they wear contact lenses, maybe wear your glasses that day. Sometimes people blink a little bit more with contact lenses. Okay? Now, if you, excuse me, if you do happen to include all these blinks, one way that they can distort the data, you can see that this is stimulus onset here, and they're blinking before. You're going to see this huge jump, because what we want to do, and we'll get to this a little bit later, is we want this to be flat here. We want this to be sort of baseline correctly. And if all this is happening beforehand, that's going to distort the whole symptom later on. So that's kind of an introduction to what we'll get to later. We've introduced this idea of saccades already, right? Where you have the electrical activity moving along, and then you have that eye movement left or right. It's kind of some examples of what that might look like. Okay? And you remember when we were drawing it earlier today, we put that little L or the R there to indicate the left or the right side that it was recording from. So we have that as some artifacts of the horizontal direction. And again, you want to design your experiments so that they don't have to deviate from fixating. So that's what we talked about earlier, right? You set your experiments so they don't have to look all the way across the screen. They maybe just use one word in the middle, right? So that's one example of why we only use one word for our stimuli. It'd be nice to see if they could remember paragraphs or sentences, right? Because that's a little bit more realistic in real life. But unfortunately, that'd give us a lot of that would interfere. Okay? So here's a couple other ones that we talked about. Here's our EKG. Ryan did a good job drawing that earlier. Our EMG as well. Okay? Really fast, high frequency data over there. So you can see that this is sort of like normal neural activity happening, and then maybe something happened and the person got a little tense. Okay? So you can start to read that in the physiological traces. Okay? Some drift, some skin potentials that we talked about. Okay? So the electrode kind of gets blocked, kind of stops recording there. And then here's an example of that alpha wave. So normal activity, and then you get this slower frequency alpha wave. Maybe they got a little drowsy on you. Maybe they were trying to take a little snooze. Okay? So that's kind of some examples of what they're going to look like. You guys did a really good job sort of corresponding drawing from the outline. Blocking. Blocking is basically where that electrode is going to kind of get blocked and no longer really be recording much from that site at the moment. Maybe it gets blocked for making contact with the skin or something like that. So we talked about rejecting artifacts as one way that we can do that. Okay. And let's see here. I'm going to skip through a couple points on this slide because we've already covered it. We're not going to get more depth on it. And so the trick here, when we're talking about artifact rejection, okay? Remember last class we talked about throwing the baby out with the bathwater? Right? You have this problem. You've got bad stuff in the data. You've got these artifacts there. Because all we care about, right, as psychologists in this situation, we care about the brain. We don't care about muscle activity. We care about the brain activity that we're measuring. Anything else besides the brain activity is stuff we don't want to know about, or at least we don't have to, we don't need to. And in fact, things that might interfere with the signals that we do want. So, we have this problem that within all the good data that we have, we also have a mix-in of bad. And we have to do that proverbial sifting of the signal from the noise, the wheat from the chaff. Okay? And so, you could do one thing, which is basically throw out all the channels if there's an artifact detected in any channel. Okay, so during a particular trial, if there's a blink or there's something happening in one of the 32 sites, you just say, oh, we can't keep this one. So you got to throw that trial out. That's one thing you can do. That's just basic artifact rejection. Okay, but the problem with that is that there's what you might call a continuum of goodness. Okay, sometimes there might be some EMG activity that could be perfectly fine to include because it'll average out over hundreds of trials. And then there might be some EMG activity that's really horrible and you definitely want to throw it out, right? Well, what about somewhere in between, right? There might be some EMG that's like, I don't know, pretty bad, but how do you decide, right? Everybody's decision criteria might be a little different. So you have some issues there. And then we also have the issue of sort of detecting the signal as well, okay? So when we basically have to measure that, so the artifact tends to be bigger when the artifact is present, and so we want that to be big when it's present, small when it's absent. And so in order to do that, we set a criterion by which we reject it. So this is a little introduction. And so anytime a trial might exceed that criterion. Now remember we talked about signal detection theory last class. Remember we talked about setting that criterion? Right? For this kind of looking at that framework now in the context of physiology. So we have a criterion for what amounts to being good and what amounts to being bad. And we already talked about how that can shift in certain situations, right? Even up here, right? Wherever that was. So there's a continuum of goodness. So we'll talk about that too. And you guys will get to reject a lot of data and figure out where you think is good data and what's bad. Okay? And again, we talked about misses and false alarms last class, and so the best criterion is going to depend on that relative balance between misses and false alarms that we talked about earlier. So let's see here. These might be some ways that you could reject some trials, okay, based on some criterion that it exceeds. I'm going to skip through a couple things here. We're not going to get into the peak-to-peak amplitude stuff. If you're interested in that, you can read about it in Steve Luck's book. But we're going to pass that over for the class right now. You can do step functions that measure how big of a change in the average happens. And if it steps down to a big enough change, then you reject it, a big enough change away from the step. Okay? That's a different way you do that. We're also not going to deal with it a whole lot in this class, but I wanted to introduce it so that you had some familiarity with it. Okay? Again, we looked at some inclusion of links and what that might look like, and how you can tell in the data if it's bad. So you don't want to see this. You want to see before the stimulus comes on the screen, you want it to be relatively strong. Okay? And so the last thing that we'll touch upon in terms of artifacts like this is the idea that we can correct the artifacts too. So remember I mentioned independent components analysis? ICA. Okay, this is one way to correct the artifact and keep the data. Okay? So in this way, you keep both the baby and the bathwater. You just clean the bathwater. So the way that that's basically going to work is that you basically, let me see if I can skip through a couple of these things here. Well, what I wanted to basically do is keep it simple and just introduce the idea that with ICA, you're subtracting that information out. So remember we talked about earlier today that because we know that there's a decay function across the scalp at a certain rate, you take that knowledge and you apply it to subtracting that value of the blink out from the rest of the head's electrode sites. And it's going to be a little bit smaller subtraction the further and further away the electrodes are from the eyeballs. Make sense? That's the simple version of what we'll talk about with ICA. And we're going to save ICA's more in-depth lecture for a little bit later in the course. We'll kind of build to that point. But for now, does that give a pretty good review of what we talked about? Okay, cool. So, then, let's see here. Give me a moment, and we will get going on the next phase. So if anyone is interested, the slides that we just reviewed were lecture 4 slides in your PowerPoint files for the lectures. Okay, so then as we get moving on this next one, were there any questions on, let's see here.